All right. Hello, everyone, and welcome to the next session at ANTS. I remind everyone that this is an invited talk, so it's recorded. The question and answer after will not be recorded. Felipe, do you consent to this recording being made public?
Yes, I do.
Thank you so much. So I'd like to introduce our speaker, Felipe Voloch, a professor of mathematics at the University of Canterbury, who will speak to us on commitment schemes and Diophantine equations.
Thank you, John. Thank you, Drew, for doing the technical stuff, and Stephen and the organizing committee for inviting me to give this talk. I was hoping to have a short trip to Auckland to see all of you in person and welcome you all to New Zealand, but there you are. We're not going to do that, but welcome anyway. So let's get started. So this talk is well, it sort of is motivated by some questions in cryptography, but is more an opportunity to ask a bunch of pose a bunch of problems in algorithmic number theory. So I think it's going to be very appropriate for this audience, and in particular there'll be lots of questions about solving the Diophantine equations, which I think are approachable and interesting, and so I'll be looking forward to getting some of you engaged in these problems and maybe giving me some answers. Okay, so what's the motivation? So this idea from cryptography that if you have something that is easy to do but hard to undo is the basis for a bunch of cryptographic protocols. So the classical one is multiplying is easy, factoring is hard, and so on. So every time you have some problem that is easy to do and hard to undo, you hope that you'll be able to use it for cryptography. But so here's the problem that is hard to do, is solving the Diophantine equations. So solving the Diophantine equations is a hard problem. So if I give you, say, a curve and say it has a rational point, you may have trouble finding the rational point. On the other hand, if I give you a point on the plane, you know how to pass a curve to that point. And if you want it to be an algebraic curve, you just have to solve a linear equation for the coefficients to make sure that that curve passes to that point. So this is an easy problem. So given a point, finding a curve through that point is an easy problem, but giving just a curve, finding a point is going to be hard. So this is one of these one-way functions that you hope might be useful for cryptography. And so can we do that? And Akiyama and Goto, about, I don't know, 15 years ago or 20 years ago, suggested this as a possible way of having an encryption system, and they had a concrete proposal, but this proposal got broken, and then they fixed it, and it got broken again, and they fixed it again. I actually lost track of where it's at right now, but it's, that particular proposal maybe wasn't perfect, but the idea is still, some of the problems in solving, in breaking the system, do not go through the route of finding the rational point. So the basic hard problem still remains a hard problem. What happened was the way that they set up the crypto system allowed you to break it if you could construct, say, an algebraic point, which is an much easier problem. So it's a question of implementation. Now, I want to talk about commitment schemes, and this is a cryptographic protocol, or a class of cryptographic protocols, which are simpler than encryption. So you're not trying to communicate, you're not trying to exchange messages. I'll explain what a commitment system is in a moment. This was a suggestion that Stephen Galbraith, our host, gave me, to look at commitment schemes as a simpler cryptographic problem that might be amenable to be used with Diophantine equations. So what's a commitment scheme? So you have something that some secret that you have that you want to commit to it. So imagine you participating in an auction and you want to put in a bid. You want to lock that bid in, and so that you cannot change it, but you don't want to reveal it to other people because that will give other bidders an advantage. But you don't, because of the rules of the auction, you cannot change your bid. And also, you don't want to submit multiple bids. So you have to have some way that you start with your message, maybe your bid, and you compute something out of this message, and you reveal the result of this computation. So you're not reviewing the message itself, you're reviewing the result of a computation. So a public value obtained from the message. And later, you want to review your message. So when the bidding closes and the auctioneer looks it up, you want people want to see that what you have originally committed to is exactly what you're revealing later. So there has to be a further calculation that checks that what you're revealing later produces the computation that you committed in the first place. This idea of using 1A functions from the Diophantine equations for commitment scheme was proposed some years ago by Bonnet and Corrigan Gibbs. I'll talk a little bit about what their proposal was. So I'm going to present two different commitment schemes from the Diophantine equations, and to be honest, I don't really know whether they are completely secure. And so your mission, should you accept it, is to break them. All right. So let me just put it up. Put the commitment scheme from the Diophantine equation in sort of a general setup. So my messages will be encoded as a point with coordinates in some field F, and the commitment, the way that I'm going to lock in my message is by constructing some variety V over the field F from some fixed family. So maybe plane curves of fixed degrees, something like that. And I choose my variety so that my secret point is in the variety. So I'll reveal the variety, and hopefully revealing the variety alone will not give you enough information to recover the point. So so what do I need? I need that given a point, I can construct the variety. So hopefully this variety, the family of variety, is a linear family of variety. So finding the coefficients that make the point belong to the variety is such a linear system of equations. So it's easy to construct the variety. Given the variety alone, it should be hard to find the rational points. So it should be difficult to obtain the point that you want to keep secret from just the variety. And finally, a very important condition, that's why it's called the commitment scheme, is that you want to make sure that your variety has only one point. Later on, I'll relax this slightly, but we'll see how it goes. But for now, think of it this way: we have this variety, and this variety should have only one point. Why? Because you don't want to cheat. You don't want to commit to several messages and then choose the one that is most favorable to you. Say in an auction, you may make 10 bids and then choose the one that wins you the auction and it's less costly to you. So whoever is running the auction doesn't want this to happen. So you cannot commit multiple messages on the same commitment. So the variety should not contain a lot of points. Should not contain, So ideally, you should have only one point. So that if you reveal, once you reveal P and check that P is in V, P was the only possibility. So you have to have some way of checking that the variety has only one point. And that maybe is the sort of new question that I have for the algorithmic number theory community is: how can you construct varieties or equations that has only one solution that you can actually see?
Yeah. Oh, wait.
Somebody is not muted. So, sorry. So, where was I? So you want to construct varieties that you can ensure have only one point, without without being able to find the points. Okay, so that's our sort of goal in general. So let's see ways of doing that. So the first way to do that was the original proposal of Bonnet and Corrigan-Gibbs. So let's go to that. So this is Harvey Friedman, who is a logician, asked for completely different reasons the following question: is there a polynomial in two variables with rational coefficients that as a function induces an injection from Q cross Q to Q? So that's still an open problem. So, if you want to think of a hard problem, that's a very hard open problem. Bjorn Poonen answered this problem modulo the Bombieri-Lang conjecture. So assuming the Bombieri-Lang conjecture, which I'm not going to state is a conjecture about rational points on surfaces, he proved that there is a polynomial in two variables, f of xy, that induces an injection, q cross q to q. Unfortunately, Bjorn's solution is non-constructive, so we don't even know what polynomial that is. It just shows that there is one. So, but if you have such a polynomial, you can construct this family of curves like this. So if you have a point AB, you compute f of AB, and you review. So if f of AB is Q, is K. So if f of AB is K, you review f of xy equal to K. So f of xy is something that everybody knows, is this injective function, and you just review f of xy equals to K. You don't review A and B, you just review K. So the question is, can you solve this equation? So given K and the knowledge that there is a B that solves this equation, can you actually find A and B? Well, of course, it depends on F, right? So let's see what possible Fs are there. So of course, Bjorn's F we cannot use because it's it's just a non-constructive proof. So there exists an F, but Zagier, upon hearing about Friedman's question, said, what about x to the 7 plus 3y to the 7th? Well, we don't know if x to the 7 plus 3y to the 7th is defines an injective function on the rationals, although it has not been observed to fail, right? So we can conjecture that it is, and it's quite reasonable. In fact, it's like almost every choice of F will work. I mean, if you just pick it randomly and you avoid some symmetries, you have an injective function. If you raise the exponent, instead if you use 7, you use 13, then you can apply the ABCD conjecture and actually prove conditional on the ABCD conjecture, show that such a function is injective. What's the ABCD conjecture? It's like the ABC conjecture, but with an extra term. And I don't want to go into a rabbit hole talking about the ABC conjecture. Let me just point out that the ABCD conjecture has not been claimed to be proved. It would require a lot more stuff. Anyway. So the question here, it would be, is solving this equation hard? And my guess is no. And so I put to you the question, do you know how to solve this equation? So if I give you K, and it's important, I tell you that there is a solution to this equation, can you solve it? Now, I think that knowing K will tell you a lot about the sizes of X and Y. Typically, for example, there won't be any cancellation between the numerator and the denominator. So the denominator of K will be the product of the 7 powers of the denominator of X and Y and so on. And one other thing that I wanted to point out before I go on is that even if you don't know how to solve this equation for every K for which there is a solution, to break the crypto system you would need to be able to solve it for most cases for which there is a solution. So
Hey, Felipe, at the risk of going down the rabbit hole, there was a comment by J. Morris Rojas, who asked, I think you said ABC conjecture and you meant to say ABCD conjecture, that there's no one that has even claimed to have proved
nobody
that
has claimed the proof of the ABCD conjecture. Mochizuki's whole strategy depends on reducing the ABC conjecture to the spiral conjecture, and that does not work for forced semantics. So not even Mochizuki has claimed anything about the ABCD conjecture. And I don't want to discuss the ABC conjecture.
I think that addresses it, so thank you very much.
Okay, so going back to this question here, can you solve this equation for most values of k for which the equation is solvable? When you're setting up a commitment scheme, you don't really have a lot of control over x and y, and you want actually the x and y or the a and b to be actual random, right? So you don't want that to be predictable, so you might want to include some randomness. So you have to be, for this equation to be useful, it has to be hard to solve in most instances, not, which is a little weaker than hard to solve in every instance, okay? And to give an example, there's a recent result of Hector Paston, which addresses Friedman's original question. He produces a curve U, and a affine curve U, and the corresponding surface S, which is U cross U, and this surface has a map to the affine line, which induces an injection from the rational points of S to Q. So that's a very nice result, and I guess it sort of addresses very well Friedman's original question, except the set of rational points on the surface S, the set of rational points on this curve U, is very sparse. It's an affine subset of an elliptic curve. So the set of rational points is very distributed, very has lots of gaps there. So if you know the size of the image, so if you know the k, so you have this f from S to A1 and f of p is k, if you know the size of k, you can recover the size of p, because there's only going to be only one rational point, only one neighborhood of rational points where you'd be able to hit k. So this result, while still very interesting, is not useful for this commitment scheme. And the question then is whether x to the 7 plus 3y to the 7 has the same issue or not, or is it safe or is it not safe? Okay. All right. So can we? But we still have the problem that this thing has not been proved to be injective. And Corneliussen, who wrote a paper again about Harvey Friedman's question, showed that he pointed out the ABCD conjecture is true for function fields of characteristic 0. So you can use that to show that a function like this, x to the m plus ty to the m, is injective in a function field k of t, where k of t is, or k is a characteristic 0. And you have to take m large enough. He used Mason's original result, which maybe the m had to be 30 or 40. If he uses better results, you can bring m down to 13, just like in the case of the number field case. Now, you can ask the same question, but can you use this to build a commitment scheme? And then you're left with this question. Is solving x to the m plus ty to the m over qt hard? And I guess my guess is that is no. And again, what we can try and do is reduce to this previous problem, right? If you can solve x to the m plus a, y to the m equals k over q, you should be able to solve this over q of t by just plugging in different values of t. So you plug in larger and larger values integer values, for example, for t, you get a bunch of Diophantine equations over q. If you can solve several of those, then you can interpolate and solve for x and y. So my expectation is that this is going to be even easier to solve than the case of the rational numbers. But I don't really have an argument at this moment on how to solve this equation. So, you know, I'd like to see if, you know, somebody in the audience will have some idea on how to solve this. Corneliuson also noted that the function. So if you don't want to use, let me just go back a second here. So there's this remark here. So Corrigan and Gibbs decided that maybe you should, instead of working with this polynomial over Q, you could work it mod n, where n is a product of two large primes, so RSA modulus. So I don't know. I mean, so one thing that they're trying to do is break this issue of the size of the number. So if you're working mod n, then size doesn't, you know, size of individual numbers just loses meaning. So that avoids this issue of the Diophantine equation being easy to solve. I mean, I don't know if this is secure or not. I don't think people have looked at it very carefully, but certainly, you know, one of the motivations, one of the original motivations for looking at alternatives to RSA or discrete logs or whatever is quantum computers. So one would hope that the crypto systems we're building with Diophantine equations is quantum resistant, because we don't know how to solve Diophantine equations with a quantum computer. But certainly reducing mod n will cease to be quantum resistant. So that would not be very useful. Now, the thing, so going back to the function field case, you know, there's over Q, there's size of numbers. Over Qt, even more so, you can talk about sizes of numbers. If you work over a function field over a finite field, then the issue of sizes become less pressing, because, you know, knowing the degree of a polynomial doesn't help you very much to narrow down what the polynomial is. So you might want to consider this question over FQT. And Corneliuson noticed that a function like this, where P is the characteristic, is injective in K of T. So x to the P plus T, y to the P is injective in K of T when K has a characteristic P. But solving this equation is very easy. And I'm just going to leave it as an exercise for those of you who want to, an easy exercise. I'm posing a lot of hard problems. So maybe I pose an easy problem for a change, and that checking whether solving the equation x to the P plus T, y to the P equals to K in FQT is quite easy. But this idea of looking at functional fields over finite fields is a good one, because it at least removes this issue of guessing the size of the numbers. Okay, so what can we do with that? Well, the ABCD conjecture over functional fields of characteristic P is not true, you know, with the same statement as in characteristic 0, but it is true if you restrict to functions of degree at most P. So something like this, x to the 13 plus ty to the 13, is injective in when x and y varies on elements of k of t minus k of degree at most P over 13. And then let's avoid 13 dividing P because of the previous thing, and 13 dividing P minus 1, because when 13 divides P minus 1, there's a symmetry, right? The 13th roots of unity will be in the field, and then you can do things like that. So, but if you avoid those situations, you get a function that is injective, but is injective in a subset of functions of small degree. And I want to make a remark that it's not injective over the whole function field, because there's this twisted Frobenius map that from one solution you can produce another solution, but the second solution that you produce has degree which is much higher than the previous one. And let me go back to to the page about commitment schemes, I had this condition VF equals 1. And now I can't use this because I'm dealing with an equation that has infinitely many solutions. But I don't need this. All I need is that the cardinality of the set of points in VF, for which the height of the point is less than little p over 13, is 1. So I don't need. So if I tell you that my secret is a point of small height, all I need for the commitment scheme to work is that the set of points of small height on my variety has only one element. Okay, so I am not solving the problem as originally placed, but if I want commitment schemes, I can restrict to equations, equations of degree at most p over 13. And since I need for cryptography, I need to have the space of possible messages has to be quite large. So I may have to take a very large finite field. But that's okay. So I just look at functions of small degree. I can take this mapping here for pairs of functions of small degree to functions of small degree and build a commitment scheme out of this. And again, my question to you is x to the 13 plus ty to the 13 equal to k hard to solve in fp of t. So I don't know what the answer to this question is. I hope the answer is yes, but yeah, I don't. Okay, so this is my first proposal of a commitment scheme. Is this one here? Now I want to move on to a second different proposal, which I have more confidence in, and also raises a lot of interesting questions. So my messages will be rational curves in P3. So I take rational curves of degree m. So I take polynomials of degree at most m, or coefficients in fq. I build this rational curve. So it's a curve like this in P3. And you can think of this also as a point. So if you want to think of this as a point, this is a point with coordinates in the rational function field. So you can think of this as a point or as a curve, depending on how you feel that morning. You know, if you want to think about points over function fields, there you are. If you want to think about curves over finite fields, you can do that too. Okay, so these are my points. And my Diophantine equations will be constant Diophantine equations. So the previous equations are not constant, but they were isotrivial. This is, takes it even further and just looks at constant. So I want to take a smooth surface of degree d containing this curve p. So I'm just going to build a surface that contains this curve. So again, this is the p is the, there's somebody typing and is not muted. So P is going to be this rational curve in P3, and I'm going to build a surface containing it. So how do I do that? So here is the description of what I want to do. I encode my message as a quadruple of polynomials of degree at most m for some m over some finite field fq. So I need to have lots of options. So I'm going to have to either take q very large or m very large. At the moment, I'm sort of tending towards the idea of keeping m 3 or 4. So m small. So I'm going to have to make my finite field a little bigger. But it may be that maybe it's working with F2 or F3 might be a good thing for other people. So in that case, you're going to have to take M to be quite large. And then I want to take a homogeneous polynomial of some degree D, and you know, I think degree 4, 5, 6 is probably plenty big, satisfying. So I guess the degree is going to be bigger than M. So it depends on what you choose for M. But if M is chosen to be small, then you can choose D to be small as well. So how do you do that? You have a bunch of polynomials. You regard the coefficients of your equation as unknowns. You plug it in, and this becomes now, you know, if you plug in a polynomial of degree M into a polynomial degree D, you get a polynomial in coefficients, polynomial in T of degree dm. You want to make sure that it vanishes identically, so you have to kill all the dm plus 1 coefficients, and this dm plus 1 coefficients are linear equations in the coefficients of f. So to find such a polynomial, you just have to solve a system of linear equations over a finite field. So that's very easy. And so I want to choose a random one because I don't want to give any hint about what the FIs are. And now there's the third issue is to guarantee that there's a unique solution. So right now, you know, again, is a similar thing. So I cannot guarantee that VF is 1. So this I cannot guarantee, but I want to guarantee that the cardinality of the set of P in VF with the height of P equal to M is 1. Okay, so I want to make sure that this surface that I define by this equation F equals 0 has only one rational curve of degree M inside of it. And to do that, I'm going to require that the surface is smooth and Picard number 2. So on the next slide, I'm going to explain how this helps. But for now, just think of it as a condition that ensures that this rational curve inside the surface is unique. So if you find the surface, so you pick one at random and you check whether those two conditions are satisfied. And if it is, you publish F as a commitment. If not, you go back and try and find a different F. Hopefully there's plenty of Fs that you can run through. And one important question is whether there are enough of those good ones that by random search you will find I'm laughing at one of the comments on the chat. You'll find a solution. And so, okay, so how do you check? So I want to check that the surface that I'm committing to has only one rational curve. So I want it to be smooth and Picard number 2. To check if a surface is smooth is easy. Magma does that for you in a second. So that's not a problem. To check that the Picard number is 2, so the Picard number is the rank of the Néron-Severi group. And conjecturally, by the Tate conjecture, it is also the multiplicity of 1 over Q as a root of the L function. So if you can compute the L function, you can compute the multiplicity. There is also an inequality due to Tate that says that the Picard number is at most the multiplicity of 1 over Q as a root of the L function, at most the analytic rank. So if the analytic rank is 2 and the surfaces I'm constructing have Picard rank at least 2, then there is the theorem of Tate that guarantees that the Picard number is 2. So I don't need to rely on the Butcher or the Dye conjecture or the Tate conjecture to use this. So if I can compute the L function, then it's okay. Right now, computing L functions is something that people have been studying. So in particular, there is a nice paper and nice software due to Edgar Costa I've been using to do calculations for degree 4 and 5. It works really well for degree 4 and 5. It begins to suffer a little. The software begins to suffer a little when you try to compute our functions of surfaces of degree 6. So I think it's a worthwhile endeavor to try and push Costa's ideas or improve the software, improve the algorithms, so you can compute L functions of surfaces of a little higher degree. The other question that comes out of this is, we're picking the surface as a random containing my curve. How likely am I to get one that fulfills my conditions? And so this is more a question of arithmetic statistics. I think the common wisdom is that the rank is as small as possible given the constraints that are being presented. But I don't know how much of that has been proved, and also I'd like to see more experiments done on that. I've done some very small scale experiments to make sure that the surfaces that I was producing were likely to work or had a fair chance of working. When I tried some very, very small examples of over F2 and F3 with degree 4, it was not working. So the surfaces were not good often enough. But once I bumped it up to larger finite fields, then things started behaving more like you would expect. So that was just a peculiarity of very small numbers. So once you move up numbers a little bit more, it appears that those surfaces, smooth surfaces with Picard number 2, are very plentiful. So it's okay. Now, here's the theorem that has been on the slide for a while. So I expect you've already had the chance to read through it. If I have a surface of some degree bigger than 3, Picard number 2, smooth, then it contains at most one smooth rational curve, as long as of degree m, as long as m satisfies this inequality. So this inequality is a little harmless. It's just m cannot be too big compared to d. Once you impose that, then this theorem ensures that the surface contains at most one smooth rational curve of degree m. And that's what we need for the commitment scheme. So the rational curve that I'm hiding inside the surface is unique. And I want to give a sketch of the proof of this theorem. It's always good to prove something in a talk. So let's give a sketch of the proof. So suppose not. So suppose you have suppose you have 2 of them, 2 smooth rational curves of degree m. So these are curves on your surface. You also have, so your surface is there somewhere. So there's one rational curve, there's another rational curve, and there's also a hyperplane section. That's the 3rd curve, which I'm going to call H. So there are 3 curves in my surface. The 2 smooth rational curves, which I'm trying to prove don't exist, and the hyperplane section. And remember, my assumption is that you have a surface of Picard number 2. That means that the non-Severi group has rank 2. And what I'm going to show is that under these conditions, these 3 curves are independent in the non-Severi group, which will give you my contradiction, right? So Picard number 2 forbids 3 curves being independent, right? So how do we check that 3 curves are independent? We compute the intersection pairing matrix. The intersection matrix. So you intersect every. So you have 3 curves, and you take intersection numbers of every pair, and you make a matrix. And if this matrix has non-zero determinant, then these 3 curves are independent. So let's compute the intersection matrix of these 3 surfaces. So remember, H is a hyperplane section. So how do you compute H squared? This is well, you can think of it as you can also compute it as H1 times H2, or H1 and H2 are 2 different planes. So 2 different planes intersect in a line. A line cuts the surface in D points. So H squared is D. So this is sort of elementary algebraic geometry, but it's fun to go through that. So h squared is d. So pretty much from the definitions of intersection pairing, the intersection of the self-intersection of a hyperplane section is d. Now, what's h d1? So you have so h is a plane, and d1 is a curve of degree m. So I'm intersecting them inside the surface. So h is the intersection of the plane with the surface. And you're intersecting everything inside the surface. But you can think of h d1 as intersecting h and d1 in P3. So you're intersecting a plane with a curve of degree m, so you're going to get m. And h d2 is also m, is the same thing, and the matrix is symmetrical, so you get the m's over here. Now I want to talk about the diagonal terms, which is the di squared. And there's this thing called the adjunction formula. Which is a sort of a generalization of the genus formula for plane curves. It tells you how to compute the genus of a curve inside the surface in terms of intersection, or in terms of this, and also the intersection of di with the canonical divisor of the surface. So the canonical divisor of the surface is d minus 4 times the hyperplane section, so that's where this d minus 4 comes in. So this diagonal terms comes from the adjunction formula, using the fact that this curve d is a smooth rational curve. Okay, so that tells you what the diagonal terms are. And the only thing that is missing is this delta here, which is the intersection of these two rational curves. I don't know what it is, so I'm just calling it delta. I don't have any control over it. I mean, I have some control over it, but I cannot tell you what it is. So my determinant is what's written there, except the deltas are not something I know. But everything else I know. But then I compute the determinant, I get the quadratic polynomial in delta, right? And I'm very lucky because this quadratic polynomial factors easily, and there are two roots that I can compute. Now, the first root is a negative number. And remember, delta is d1 times d2 is the intersection of these two rational curves. It's an intersection number of two distinct curves. This is non-negative. Right? It's just counting, literally counting how many times the two curves intersect. So this negative value, negative root of my quadratic polynomial cannot be the intersection number of these two curves. The other root is positive, but fortunately it's quite big. It's bigger than m squared. And remember, these two curves have degree m. So they intersecting at most m squared points, like by Bezout, right? You can project to a plane. I mean, it's a space curve, so they maybe they don't intersect at all. They intersect just at 1 or 2 points. But if you project to the plane, you know that the projections are going to be plane curves of degree m, and then you can apply Bezout on the plane, and then you get the number of intersections in the plane, which are projections from the intersections up there, or projections of other things, is at most m squared. So this delta is less or equal to m squared. And the assumption of the theorem, this inequality here, is there precisely to make this number bigger, this other root delta bigger than m squared. So the two possible roots of this, two possible zeros of this intersection matrix cannot be the intersection number of these two curves. And so that proves the theorem. And that's pretty much what I wanted to say. So thank you very much for your attention.
Thank you, Felipe, for that very stimulating talk. Everyone, let's give him a round of virtual applause, however you wish to do so. And we've had some, yeah, thanks very much.